I have achieved full corporeal form again, no longer see-through, and we're going to do some problems from the book. Trying to do a lot of problems here, so you might be in here for a while. Don't watch all of it at once. You can just watch problem by problem as you have questions. We're going to start with number 90, which says that in pre-calculus, you hopefully learned a formula for the position of the maximum or minimum of a quadratic function. And that maximum was at negative b over 2a. And the question is, can you prove that there is a maximum or minimum here, an absolute maximum or an absolute minimum here using calculus? Well, for an absolute maximum or an absolute minimum, that can only occur at the endpoints or at critical points for a continuous function. All right. So, or even for a non-continuous function, it just might not exist. So for this one, let's just find the endpoints and find the critical points. So y equals ax squared plus bx plus c. Again, the candidates are going to be at the endpoints, but what is our domain here? Our domain is negative infinity to positive infinity. So when we look at these ends, right, the limit as x goes to positive infinity of this function, well, that's either going to be positive infinity or negative infinity. Let's just say, let's just assume a is, well, no, let's not assume anything. It's positive or negative, depending on what's the case. If a is positive, right, our parabola looks like this. It goes to infinity in both directions. If a is negative, that's what we have. And actually, we have the same thing. We can kind of edit this a little bit. As x goes to either positive or negative infinity, it goes in the same direction. Which means that if a is positive, there is no absolute max. If a is negative, there is no absolute minimum, because it will always go further and further down. So the candidates are going to be, our only candidates are our critical points here, because there are no endpoints. So find the derivative and see when it's undefined, and see when it equals 0. Take the derivative with the power rule. Remember that a and b and c are all constants. It's always defined, right? It says always defined. So we only have critical points when the derivative equals 0. Well, when is that? Let's subtract b from both sides and divide both sides by 2a. Oh, there's a critical point when x is equal to negative b over 2a. So there's definitely a critical point here. It does remain to show that there's an absolute maximum or an absolute minimum. Right? And that takes... so if a is positive, right? A is positive means no max. But that means that this is a min. And similarly, if a is negative, then it's going to be an absolute maximum. And that corresponds to also what we talked about in pre-calc, right? A is positive, there's an absolute min. A is negative is the other situation as well. Okay, so I think we've just proven this. I think we've showed everything it wants to show. Prove this formula using calculus. We have shown that there is indeed an absolute maximum or an absolute minimum here. And we've also talked about when it's an absolute maximum and when it's an absolute minimum. We've done exactly what it wanted. There's no boxing of our answer, because our answer is this whole process. Let's look at number 106 next. Draw graphs of a function that is also continuous on the interval -4 to 4 with the following properties. F should be continuous on negative 4 to 4. That's important. We need to incorporate that. And 106 says it has an absolute maximum at x equals 4. So when x equals 4, that has to be the tallest point in this whole interval. Absolute minimum at x equals negative 1. There's a lot here. Local max at x equals negative 2. And critical point that's not a max or a minimum at x equals 2. Okay, so let's try to make a graph that has all of this stuff. And the way that we're going to do that is we're just going to make a guess. We're going to try to do it. And then afterwards, we're just going to check and verify that each one holds. And again, we're only looking from negative 4 to 4. We're only looking on this interval. I don't think it has to be defined outside of this interval. Yep, it's only asking for something on this interval. It has to be continuous. Let's keep that in mind. The biggest is at 4. So let's just draw a point way up here at 4. We know the smallest has to be when x is negative 1. So let's draw a point down here. And especially with how I've written it, these are really great choices because it is hard to get above this point because I'm running into this text. It's hard to get below this point because I'm running off the screen. So these are good choices for the y values. It doesn't matter. It didn't tell us what the y values had to be, but just try to choose something that's going to be the biggest and it's going to be the smallest. So next up, there has to be a local maximum at x equals negative 2. So there's a local maximum here at this x coordinate. There's a couple ways that could appear. You could incorporate that at x equals negative 2. You could have it be something like this. This would be a local maximum here. You could have something be like this. This is a local maximum here. A couple different ways that you could draw it, but put it here. And again, it doesn't matter whether it's here, whether it's here, whether it's here. It doesn't matter where it is. What matters is that there's a local maximum here. There's also a local minimum. Sorry, there is no local minimum actually. There's a critical point at x equals 2. And again, that could either look something like this, horizontal tangent line, but no max or min. It could look like this, vertical tangent line, no max or min. It could look like, I was going to say it could look like this, but now it's not continuous. So we do need to have things continuous. So again, you can do whatever you want when x is 2. Just make it look something like that. And then we can just connect these kind of any way that kind of makes sense. Oh, wow, that's too steep. Here, I want to make this smaller. I don't want to have to draw something that's steep. All right, could look something like this. Maybe. This is just the first draft, guys. Just the first draft. Let's check each thing again. You have to check each thing again. Make sure we didn't accidentally mess something up. Because there's a lot of things going on here. Is this function continuous on the interval? Yes, it's continuous. I can draw the whole thing without lifting up my pen. Is the absolute maximum when x is equal to 4? Yes, this is the absolute biggest point around. No, absolute biggest point, period. Is there an absolute minimum when x is negative 1? Yes, this is the absolute smallest or lowest point. Is there a local max at x equals negative 2? Yep, there's a local max right here. Is there a critical point at x equals positive 2? Yes, there's a critical point that is not a local min and not a local max. We have indeed incorporated everything. There's a bunch of different ways that your graph could look. It doesn't have to be curvy at all, honestly. Another graph that you could have drawn is just could have done like this, and this. No, that would be a local minimum right there. You could change the slope like that. So it's still, the derivative's not defined. You can go down here, down like this. This would also be a graph. But I think it's usually easier to draw just like polynomial looking things. That's how you do this sort of problem. Let me know if you have questions about that, because there really are a lot of possible answers to 106 in those types. Uh, 134, find the local and absolute max and minima over the interval. And I'm pretty sure for this chunk, I only asked you to find absolute extrema. Yes, I only wanted you to find the absolute extrema here on the interval from negative infinity to positive infinity. X squared minus 1 over x minus 1. Looking for the absolute max and the absolute minimum, if they exist, on negative infinity to positive infinity. So if it's continuous, on a closed interval, we're guaranteed absolute maxes and mins. This is not continuous. There's a hole. And it's not a closed interval. So we're really going to have to be very careful. So let's look at the end behavior. Again, normally we'd start with checking the endpoints, but there is no endpoint, right? This is going off. So we're going to look at those limits. These are the things that if these guys win, if these limits win, then there's going to be no extrema. So the limit as x goes to infinity of this function. This is a rational function. A couple of different ways of doing this. One of the ways is to just look at the, if you remember back from your pre-calculus days, one of the ways is to graph this. One of the ways is to look at the leading terms of each polynomial, and it's going to have the same end behavior. So the leading term is going to be x squared over x. So this is going to have the same end behavior as x squared over x. It's going to have the same end behavior as x. So this is going to be positive infinity. And as x goes to negative infinity, again, it's going to have the same end behavior as x. So it's going to be negative infinity. Okay, so right off the bat, we know there's no absolute extrema. It's maybe not a great choice of problem, because there can't be absolute extrema. There's never going to be any, oops, I circled the wrong thing. There's never going to be anything bigger than the function as it goes to infinity. There's never going to be anything bigger than the function as x goes to the left. But let's just say, for practice sake, these would be two of our fake candidates. If these guys win, then nobody wins. These are the bad candidates. We have to compare these with the actual critical points. So normally you'd be done with this problem here, but I want to show what would happen if this weren't the case. So critical points, we're going to have to look at this derivative. Oh, we're going to have to use the quotient rule. And you might say, Jason, why don't we just simplify? And again, this is kind of a tricky situation because, yeah, this is y, x minus 1, x plus 1 over x minus 1. And as long as we have our domain, right, our domain is a set of all x such that x is not equal to 1. So as long as we keep our domain in mind, we actually can simplify here. Otherwise, we could use the quotient rule. They're both fine. So this is actually our function, but it still has the same domain. So if you're simplifying this way, make sure to not lose track of the domain. There is a hole in this function. Function looks like this. That's why there's no absolute max and no absolute min. All right. And you could solve this. Eventually, you're going to find that there are no critical points. The only place where this derivative is undefined is here, but that's not in the domain. All right. So that's kind of what you can do in these ones. That's maybe not a great example though. Let's apply this for like 129. 134 is similar to 133, so hopefully that helps. And let's just look at 129 together, which also is similar to something that we did before. Y equals x squared plus 4x plus 5. So again, we have to look at the end behavior because we're looking for absolute extrema on this interval. So the limit of this function, limit of y as x goes to the left. Well, this is a parabola with a value being positive. So to the left, it goes to positive infinity, and from the right, it also goes to positive infinity. So right off the bat, we know there's going to be no absolute max. Because no matter how big we get, we can always go bigger. But to find the absolute minimum, we're going to find critical points. So we look at critical points. Critical points is when the derivative equals 0. That's going to be when 2x is negative 4 or when x is negative 2. So that's a candidate for a local max, a candidate for a global max and a global minimum. And then you just find the function value here. When x is negative 2, the function value is 4, minus 8 is negative 4, plus 5 should be positive 1. Right here, and you could check your answer here. So once you find all the candidates, you look at the end behavior, and you look at the candidates and say, what's the biggest? The biggest is infinity. Since this is at the end of an open interval, it's not included, there's no absolute maximum. Then we'd say, what's the smallest? Well, out of these two candidates, one is smaller than infinity. This is going to be our global or absolute minimum. So we'd say absolute min of 1 at x equals negative 2 and no absolute max. And that's our answer. Let me know if you have questions about that one. We'll also look at 136. Use a calculator or Desmos to graph the function and estimate the absolute and local extrema. Then solve for them explicitly. This is going to be y equals x plus the sine of x. Let's find this graphically, absolute and local extrema. So right off the bat, there's not going to be any absolute extrema, right? This gets bigger and bigger and bigger forever. But it looks like there's horizontal tangent lines here. It looks like there's critical points here. But we're not looking for critical points here. We're only looking for absolute and local extrema. So in this case, there's no absolute extrema. There's no local extrema. Again, these are critical points, but not local extrema. This is not a local minimum because to the left, it gets smaller. It's not a local minimum because to the right, it's not a local maximum because to the right, it gets bigger. So actually, there are no absolute or local extrema. And again, another way you could find this analytically is you could look at the limit as x goes to infinity is going to be positive infinity, no global max. The limit to the left is going to be negative infinity, no global minimum. And you could find critical points. And you could find that there are indeed critical points, infinitely many, whenever cosine of x equals negative 1. But again, and we'll show why in the next section, 4.5 will show that analytically, these critical points are not extrema. In the meantime, we're going to be using graphical methods for local extrema in this section. That's how you approach these sorts of problems. And again, looking at something like 135 or something, you would just do it graphically and then find these things by taking the derivative. Let's end with 144. I think 144 is going to be a good one. Find their critical points and absolute extrema for the following. And our function is a piecewise function, x squared minus 4x and x squared minus 4. We use the top piece when x is between 0 and 1. We use the bottom piece if x is between 1 and 2. So right off the bat, are we guaranteed with the extreme value theorem, are we guaranteed a max or a minimum? The extreme value theorem guarantees us a maximum and minimum if we're on a closed interval, which we are, 0 to 2, and the function's continuous. This function may or may not be continuous. Each piece is continuous. Remember back to chapter 2. So since each piece is continuous, this function is going to be continuous if they meet in the middle, if the pieces connect. We look at the function value, which is using the top piece when x is 1, and we look at the limits for the bottom piece when x is 1. Function value is 0 here. The limit from the right is going to be -3. Oh, okay. So function value is different from the limit. The limit actually will turn out not to exist because there's the one-sided limits are going to be different. So the two-sided limit doesn't exist. So this is not continuous. So we're not guaranteed an absolute max or min. And honestly, you don't even need to do that in this problem, but I'm just trying to connect to different concepts. So we need to find critical points and we need to find absolute extrema. So let's start with our candidates for absolute extrema. Absolute extrema can either be at the endpoints or at critical points. So what are the endpoints? Well, that's going to be when x is 0. Let's write these in green. And when x is equal to 2. When x is equal to 0, the function value. Oh, wait. I lied to you guys. The function value is when x is 1, which is not 0. When x is 1, this is 1 minus 4, which is -3. This is continuous. So we are guaranteed an absolute max and absolute min. Huh. All right, so these are the endpoints. 0, 0, and 2, also 0. Right, when x is 2, we're on this bottom piece and we get 4 minus 4, which is 0. So these are the endpoints. These are two of our candidates for absolute extrema. We also have to look at the critical points. And that's a little harder here. Critical points are when the derivative equals 0 and when the derivative doesn't exist. Let's start by looking at when f prime of x equals 0, and then later on we'll look at when the derivative doesn't exist. So the derivative of this function is a little tricky. We haven't talked too much about derivatives of piecewise functions, but the derivative will also be a piecewise function. It's going to be 2x minus 4, the derivative of the top piece, sometimes. It's going to be 2x, something else, and it may or may not be defined where they open up. Graphically, for piecewise functions, if something like piecewise function like this is continuous, but it's not differentiable where the pieces meet. But it could be something like this, where this is also a piecewise function, and the derivative does exist, because the slope from the left is 0 and the slope from the right is 0. So really, to know analytically whether the derivative exists here, is a complicated question. Honestly, if you wanted to skip some steps, you could just say, I don't know whether it exists or not. Let's just consider it as a candidate. You could do that. But I think it's good practice to not do that. So again, right off the bat, we know this is going to be true when we don't include 1. The question is this also the derivative at 1? Well, when x is 1, is the slope the same from the left and from the right? When x is 1, is the derivative the same from the left and from the right? Well, from the right, that's the bottom piece. The slope is going to be 2 from the right. From the left, that's the top piece. When x is 1, slope is going to be -2. So the derivative does not exist when x is equal to 1. Actually, that takes care of our second check as well. F prime does not exist when x equals 1. Boom, we got another candidate. 1, -3. And we also want to know when the derivative equals 0. So to solve this, we're just going to look at each piece and make sure that any candidates that we have are in that piece. So f prime of x equals 0 when 2x minus 4 equals 0 on the interval from 0 to 1, and when 2x equals 0 on the interval 1 to 2. Right? We're only looking at our domain. Our domain is just 0 to 2. And so we're looking when this slope equals to 0 on this interval, or when this slope equals to 0 on this interval. So solving this first one, this is going to be when x is equal to 2. Well, that's not helpful. That's not a candidate because it's not in that portion of the domain. When x is equal to 2, we're using some completely other slope function. Right? This is only our slope function when x is between 0 and 1. And this other one, this is when x is equal to 0, but again, that's not helpful either. So the derivative will never equal 0. Again, if we looked at this function defined on all real numbers, yeah, it's a parabola. It'll have a horizontal tangent line. And this one, if we looked at it for all real numbers, would have a horizontal tangent line somewhere as well. But they're not going to have horizontal tangent lines in these places. So the piecewise function doesn't have any horizontal tangent lines. So we only have 3 candidates. These are imposters. They're trying to sneak in here. But they're not actually candidates because they're not in our domain. So 3 candidates, pick the biggest, pick the smallest. Oh, wait, both of our endpoints are the biggest. Huh, that's kind of a weird situation. These are both the biggest. And it's the smallest. Okay, so we have 2 absolute maximums. So we're going to say, well, technically there's only one absolute maximum, right? Remember our wording. Absolute max is the y value. But it'll occur in 2 different places, when x is 0 and when x is 2. Our absolute minimum is again that y value. The minimum is -3 when x is +1. That's part of our answer. The other part was asking about the critical points. Critical point was when x is equal to 1. There's 2 ways of finding critical points, both of them in blue. The first way didn't ever happen, but the second way did. The critical point was 1, -3. It's only one critical point, and it's 1, 3. Let's graph this. and see it in action because I'm feeling weird about this. So I also want to see it. And it's a good habit for checking your answer. So it's a piecewise function, and it's x squared minus 4x from 0 to 1. Inclusive. So we're going to have closed circles at these points. It's including these. And then we're x squared minus 4 from 1 to 2. From 1 to 2. 1 is not included. So normally we draw an open circle there, but we don't need to draw an open circle because it's continuous. And you can see everything that we talked about, right? You can see the glow. Oh, wait, hold on. Let's have a closed circle at 2, 0 because it is included. We said there was a global maximum of 0. The biggest y value we ever hit is 0, and we hit it 2 times. There it is. We said there's a critical point down here. We also said this is a global minimum at 1, -3. The derivative doesn't exist. The slope from the left is going down. The slope from the right is going up. There's a sharp point right here. Derivative doesn't exist. That's a critical point right there. It all ties together. Check your answers by graph, and this is kind of cool. A little happy about this. And that's how you approach these piecewise functions. I wish there were more of them, but you're probably glad there's not. Have a great day, and please reach out if you have any questions. Bye-bye.